Section 1.2, the scientific method. All sciences, including the social sciences, employ variations of what is called the scientific method, a systematic approach to research. For example, a psychologist who wants to know how noise affects people's ability to learn chemistry, and a chemist interested in measuring the heat given off when hydrogen gas burns in air, follow roughly the same procedures in carrying out their investigations. The first step is to define the problem. Sometimes this is called observation. In other words, observe something and wonder why. From that comes the problem. The next step includes performing experiments. Well, you need a hypothesis first. You need to have some kind of idea of what's going on. Then you're ready to perform experiments to validate it, or not. You make careful observations during this process, and you record the information or the data about the system, the part of the universe that is under investigation. Well, that's broad, the whole universe. In these examples, the systems are the group of people the psychologist will study, and a mixture of hydrogen and air. Weird how we have to define the system, the universe, things like that. The data obtained in a research study may be both qualitative, no numbers, consisting of general observations about the system, and quantitative, which is generally better, comprising numbers obtained by various measurements of the system. Chemists generally use standardized symbols and equations in recording their measurements and observations. Fine. This form of representation not only simplifies the process of keeping records, but it also provides a common basis for communication with other chemists. That's nice. Figure 1.1 summarizes the main steps of the research process. You observe, you represent it somehow, and then you interpret. Fine. When the experiments have been completed and the data have been recorded, the next step in the scientific method is interpretation. Well, that sounds important, meaning that the scientist attempts to explain the observed phenomenon. Yeah, that's always, well, can be challenging. Based on the data that were gathered, the researcher formulates a hypothesis or a tentative explanation for a set of observations. That's your first guess as to why things might be. Your educated guess. Further experiments are devised to test the validity of the hypothesis as many ways as possible, and the process begins anew. They always point out that this is a cycle. I prefer the observation, hypothesis, experiment, conclusion sort of cycle, but this works fine too. After a large amount of data has been collected, it's often desirable to summarize the information in some concise way as a law. Yeah, good luck. Laws don't come by very often. If you're doing research, it's not likely you're going to end up formulating a law. In science, a law is a concise verbal or mathematical statement or relationship between phenomena that is always the same under the same conditions. Coming up with a law is like the gold standard. It's like understanding nature in a primary way. For example, Sir Isaac Newton's second law of motion, which you may remember from high school science, says that force equals mass times acceleration. There's a fundamental concept. What this law means is that an increase in mass or in the acceleration of an object will proportionally increase the object's force, and a decrease in the mass or acceleration will decrease the force. Fine, but that's not even chemistry. Hypotheses that survive many experimental tests of their validity may evolve into theories. Now, a theory is a unifying principle that explains a body of facts and or those laws that are based on them. I always thought of a theory as something that might be on its way to law. Theories, too, are constantly being tested. If a theory is being disproved by an experiment, then it must be discarded, or modified, much more likely, so that it becomes consistent with experimental observations. Proving or disproving a theory can take years, or perhaps even centuries. Yikes. In part because the necessary technology may not be available. The atomic theory, for example, which we'll study in Chapter 2, is a case in point. It took more than 2,000 years to validate those findings by Democritus, an ancient Greek philosopher. I think they're really talking about perhaps the first images that showed up that verify that atoms exist. Some 100 years or so earlier, they came up with convincing evidence that they exist, the work of Thomson and Rutherford, among others. Scientific progress is seldom, if ever, made in a rigid step-by-step fashion. Sometimes a law precedes a theory, sometimes it is the other way around. I think that's true. Two scientists may start working on a project with exactly the same objective, but may take drastically different approaches, and that's fine. They may be led in vastly different directions. Scientists, after all, are human beings. Yay! And their modes of thinking and working are very much influenced by their background, training, and personalities. The development of science has been irregular and sometimes even illogical. Great discoveries are usually the result of the cumulative contributions and experience of many workers. I think they're starting to point out the importance of research. You can't just start studying something without finding out everything that has been done before you. Otherwise, you are wasting your time. Even though the credit of formulating a theory of law is usually given to only one individual. Yeah, that's a good point. And what happens in the East might get lost by the West, especially some long time ago, for example. There's, of course, an element of luck involved in scientific discoveries, but it has been said, and scientists love this saying, chance favors the prepared mind. I mean, those people that work on it intelligently are more likely to get lucky. It takes an alert and well-trained person to recognize the significance of an accidental discovery. Yeah, that's true too. You might be making one and just miss it and take full advantage of it. I think that's a very important point. More often than not, the public learns only of spectacular scientific breakthroughs, not the boring stuff. For every success story, however, there's hundreds of cases in which scientists spent years working on projects that ultimately led to a dead end. Very, very true. Many positive achievements came only after many wrong turns and at such a slow pace that they went unheralded. That's true. When things get discovered over such a long period of time, it just is not quite newsworthy, is it? Yet even the dead ends contribute something to the continually growing body of knowledge about the physical universe. It's the love of the search that keeps many scientists in the laboratory. That's a nice place to end. This is part 1.2.